I just had to let you know you're.
Assalamualaikum warahmatullahi wabarakatuh and very good day to everyone. Today we are going to dive into a very fascinating chemical concept that is vital to both our biology and our daily routine, the zwitterion. So what exactly is zwitterion? Let us start with a brief introduction to this molecule. Zwitterions are actually molecules that carry both positive and a negative electrical charge at the same time, but because of those opposite charges perfectly cancel out each other, the molecule remains in a complete natural state overall. To understand why this matters, let's look what we call the pH challenge. In our body, they are very highly sensitive to ecosystems. Human blood, for example, must strictly stay at a pH exactly 7.4. Zwitterions step in as a master stabilizers to make this happen. They serve as a natural buffer to our bodies, protecting blood proteins from dangerous pH swings. They help proteins maintain their very specific 3D shapes, actively preventing them from unfolding or clumping together. But this isn't just internal biology, it's everyday life. This exact same chemistry explains why eggs turn to solid when they are cooked, how life-saving medical drugs are formulated to work, and even how enzymes in your laundry detergent clean your clothes. Zwitterions might be microscopic, but their impact is massive.
Now, I will talk about the key chemistry concept of how the zwitterions maintain the protein stability in our blood. The main chemistry principle here is the amphoteric property of the zwitterions, which this means that the molecules act as an acid and a base. So this unique ability allows the protein to maintain their isoelectric point. And you may ask, what is the isoelectric point? The isoelectric point means that the state that the protein is most stable and electronically balanced. Furthermore, if you look at the molecular structure diagram between the transition from amino acid to zwitterions, so in our blood at pH 7.4, the carboxyl group will lose one proton while the amino group will gain one. So this creates a dipolar molecule which once will carry the both a positive and a negative charge and allow them to remain the net neutral in our bloodstream. Besides that, this diagram structure will lead to our reaction mechanism, which the zwitterions provide an amphoteric response as they act as an buffer by accepting or donating the protons to neutralize the pH spikes. And beyond the buffering, these opposite charges will create a swap bridge. And you can think of it as like molecular staples that lock the protein into its functional 3D shape. So it can prevent it from clumping or unfolding in the blood. And lastly, we will use the Henderson-Hasselbalch equation to mathematically track this balance, as you can see in the diagram. And that's all from my part, the key chemistry concept. I will pass it to Sarah for the next part, which is the real-life application. Thank you.
I'm Atika Maisara, and right now I will explain the real life application. There is three categories. The first category is medicine. For example, protein-based drugs such as insulin and antibodies. So basically, the amino acid in protein exists as deuterion. It is to help stabilize the protein structure and to maintain the correct shape. And now for the second category is the industry. So for example, the enzymes used in detergents and biotechnology. Many industry use enzymes which are protein that is in form of zwitterionic form. So it is to maintain the stable structure of enzyme and to function efficiently in breaking down stains. And for the last category is daily life. For example, cooking eggs and food proteins. So basically, the egg white contains proteins such as albumin that contain amino acids in zwitterionic form. It is to help maintain their folded structure, or when the heat or extreme pH is applied during cooking, the protein denature and it will cause the egg to change from liquid to solid.
Group analysis or prediction. The advantages: protein stabilization, prevent proteins from denaturing in blood. Next, biocompatible, the low tendency of protein absorption, making it suitable for biomedical applications. Next are the limitations: the poor solubility in non-organic solvents, which is the insufficient attraction to break apart the internal ionic lattice. Next is the sensitivity to pH. The extreme change in pH in blood can alter its effectiveness. Moving on to the future development or trends, Zwitterions can be used as a drug delivery system. Zwitterions can release drugs to a certain infectious area or body when it is under a certain pH. It can also be used in consumer products. Zwitterions are highly attracted to water, which is suitable to be used in contact lenses. Last but not least, the impacts on health, society, or environment. For health, it can improve biocompatibility in medical devices. For society, it can boost economic growth and job opportunities. Last but not least, for environment, it can act as water purification, as Zwitterions attract water molecules strongly.
In summary, a Zwitterion is a molecule that has both positive and negative charges, but is overall neutral. They are amphoteric, meaning they can act as both an acid and a base, and are more stable at the isoelectric point. Zwitterions are important because they help maintain blood pH and act as natural buffers to prevent sudden pH changes. They work by accepting or donating hydrogen ions and forming internal ionic bonds that stabilize protein structure. They are used in medicine, industry, and daily life, especially in protein-related processes. Overall, Zwitterions are important for stability in biological systems despite some limitations.